Here's the first problem that we will work in this session. I chose to go on to problem number 2 in the interest of time. We have a control system has the following open loop transfer function. In other words, this is equal to G times H. GH is 10, S plus 2 over S times S plus 20. We'd like to prepare an amplitude plot for the Bode diagram. The first thing to do, I hope you remember, is to put this into the Bode form. And by that we mean we have to rewrite this as 10, pull out the 2, S over 2 plus 1, then S, when we pull out the 20, S over 20 plus 1. We now combine these constants into one constant, which conveniently is equal to 1. So we end up with S over 2 plus 1 divided by times S over 20 plus 1. This is a type 1 system. And the type 1 system is characterized by the fact that it starts off, here's dB, there's omega. We'll have a line that has a slope of minus 20 dB per decade. So this is the way it's going to start. If I have the right slope, that's no problem. But I need a point to pass that slope through. So the point is, I look to see where omega is equal to 1. Because at omega equal to 1, this term in here will cause the gain to be equal to 0 dB. Remember now, this is equal to 20 log base 10. Case of B is equal to 1, so it'll contribute nothing in terms of decibels. 20 log base 10, absolute value j omega over 2 plus 1 minus 20 log base 10, absolute value of j omega, minus 20 log base 10, absolute value j omega over 20 plus 1. So this is really what we're plotting now, because we've now put everything in terms of decibels. And so this term I'm plotting here is really the second term in here. The one says minus 20 log base 10 j omega. Forget the j, and that term passes through 0 dB when omega is equal to 1. Now I could extend this line in both directions as needed. And the next thing I look for is to see where are the other break frequencies. Notice I have one over here that's going to occur when omega is equal to 2. I'll have a break frequency there. And I'm going to have a break frequency when omega is equal to 20. Now when omega is equal to 2, that is in the numerator. That will cause the slope of this line to change from minus 20 dB per decade to being flat, because this essentially cancels out the effect of the line that's already going down. So I go over here to where I have 2 radians per second, and at this point, where omega is equal to 2 radians per second, I change the slope and becomes flat like this, and remains that way till I get out to 20, which may be somewhere out here. And at 20, because of the presence of this term in here, because of the presence of this last term, it will go down again at a slope of minus 20 dB per decade. So the curve of the Bode plot looks like this. The only point that's critical is that this is passing through 0 dB when omega is equal to 1. So it's a very easy curve to plot, and you would just one line segment, 2 line segments, 3 line segments, and we're finished. In part B, we would like to find the steady state position error to unit step input when the system is operating in a closed loop. Assume unity feedback. Well, when we assume unity feedback, it means that H is equal to 1, and I can take this out of here for now. And the error, steady state error, if you recall from the review session, is given by the limit as S goes to 0 of S times R over 1 plus G. GH, but H is equal to unity this time. And this equation will work for you every time. There are no limitations, no approximations. But now we're given that R, the input to the system, is a unit step. So that means that R is equal to 1 over S.